Welcome back, everyone. What we're going to see now in this specific lecture is related to time-dependent perturbation theory, which is something extremely useful in many areas of physics uh, because more often than not, you are going to encounter problems that are not exactly solvable. So, to start with, our main motivation is to deal with problems that are not exactly solvable, that are time dependent, but they are close enough uh, to solvable ones so that we can perturb the system and we can apply this time dependent perturbation theory. So just to start with, normally you have exactly solvable Hamiltonians in case you have them. And we all know that if you want to describe the time evolution of a system, we have to use the time-dependent Schrodinger equation. So the question is, if we assume that H is constant in time, so it's not time-dependent, and we know how its spectral decomposition is, namely we know the eigenvalues ak of H, and we know the eigenvectors psi k of H, this means that we can write this time-dependent state vector psi t as a sum over k of exponential minus I ekt divided by h bar, where these are the eigenenergies, ck and phi k. So this is like a weighted sum, or if you wish, a coherent superposition over this eigenvector basis. And if we write it like that, we know that these coefficients here in this case are constant. And these phases come from the fact that we apply the time evolution operator to these guys. So it's pretty much what we have seen previously, that you apply a closure relation with regard to this eigenvector basis. And then you can decompose your psi t, which is the wave function you would like to evolve, or in this case the cat, because we haven't tied our representation, onto the eigenstate basis. So the question we're going to ask in this lecture is what happens if we cannot calculate the Hamiltonian's eigenvectors and eigenvalues, because sometimes you cannot. If you can, nice, it's exactly solvable. There's absolutely no issue. But this is like more the exception than the rule. So, for instance, if you are dealing with a Hamiltonian which has an interacting, which is representing an interacting many-body system, which occurs in many areas, atomic physics, molecular physics, condensed matter physics, just to name a few. You are faced many times with a many-body system that you're going to have to model. Or if you have a time-dependent Hamiltonian, which can be also tough to solve, like for instance in my area, which is strong field and attosecond physics. All our Hamiltonians are time-dependent. And in most cases, there are no analytical solutions. So what do? Sometimes you get lucky, because the solutions of these Hamiltonians, they may be close, up to small corrections, to those of a problem you can solve exactly. And that's why you say you perturb around that problem. Say, if there's a Hamiltonian H naught whose behavior you can describe exactly, and this full Hamiltonian is going to add corrections to that, then you'll be able to use perturbation theory. And so far, in your undergraduate course, you have only seen time-independent perturbation theory. And what we're going to see now is related to time-dependent perturbation theory. So let us consider a Hamiltonian that we cannot solve exactly, composed of this Hamiltonian H naught plus lambda Vt, where this is going to be our perturbation. So we have a time-dependent Hamiltonian. Here we have H naught that is time independent plus this term, which is not going to be dominant in our case. So H naught is exactly solvable. We know its eigenvalues, we know its eigenvectors. Lambda is a real parameter, which can be made arbitrarily small if you need to expand things. We're going to see this soon. And Vt is a time-dependent Hamiltonian. So we want to solve all of this. In some cases, it's tricky. In some cases, this is huge, and you cannot make this decomposition. But if Vt is weak, meaning if its matrix elements are much smaller than the energy differences associated with H naught, this is going to mean that the energy scales of Vt are much smaller than those of H naught. So that you are going to have corrections around whatever values that you will be able to get exactly for H naught. And in fact, if you have no perturbation, we know we can write our Hamiltonian like this. We have just discussed it, because then you have H naught, you can solve it. You are assuming that phi k are the eigenvectors of H naught, and ek are the eigenvalues that you get associated with that. You have the time evolution operator, and then you apply this. So what we're going to do is then have a look at how we can express this considering the full Hamiltonian. We're going to start and discuss here what is Xerox method for doing time-dependent perturbation theory. And our starting point is going to be to represent and to write our state vector in the interaction picture, and then we're going to expand into the eigenstates of H naught. So when we do this expansion, what you have to do is insert here the closure relation. You get this CJT, you have phi j, and these coefficients here, they are time dependent. Notice that if the coefficients were not time dependent, this would be like the previous case in which the perturbation didn't exist. So in this case that we are treating now, in which the coefficients are time dependent, we refer to it as Dirac method of variation of constants. So if you want to think about it in some kind of loose terms, this would be as if you were now, due to the presence of the time-dependent perturbation, varying the coefficients which, in the absence of the perturbation, were constants. If you would have written this in terms of the Schrodinger picture, where you have then that you apply the transformation, which is the opposite of, which is actually the time evolution operator associated with H naught on psi I, which is the state vector in the interaction picture, you would have found then that you have a sum over these time-dependent coefficients multiplied by these phases, which are associated to the eigenvalues of H naught, which you would get by applying this operator to phi j. And it's similar to the previous expression, just has some extra phase shifts, so we're not adding too much to the dynamics, and once more shows you that the interaction picture in many cases is advantageous. And what we're going to do is we would like to solve the time-dependent Schrodinger equation in the interaction picture. So this is the Hamiltonian in the interaction picture, as we have derived in our last lecture. This is the time derivative of the wave of the state vector in the interaction picture. This is the state vector in the interaction picture. So this is what we're going to solve. And what I'm going to show next is that this will lead to coupled differential equations for those coefficients when you consider that expansion in terms of the eigenvectors of H naught. And here we're going to have that this VMKT are the matrix elements of that perturbation V, and they are time dependent. And these WMKT that appear here, which are proportional to the difference of the energies divided by H bar, are Bohr angular frequencies, which are going to be associated with transitions between bound states. We're going to get that and we're going to discuss. And all this is associated then with the eigenstates of H naught, which is the unperturbed Hamiltonian. And note the following as well, that we will have to solve these coupled differential equations associated with these coefficients. Note as well that in the expression that I have shown before, H naught doesn't appear. You just have something related to the interaction. And you rewrote the interaction Hamiltonian then in the interaction picture, but you don't have H naught. And this is a strength of the interaction picture because it makes our life easier. And so far, we have not performed any approximation. So these equations, they are still exact. We have just used some expansion of the time-dependent state vector in an eigenstate basis of H naught. We have not expanded anything. We have not approximated anything. So far, these coupled equations are exact, but to be able to solve them, you're going to have to do some approximations. So next, we're going to see perturbative expansion. So now we are going to specifically show how we derive those differential equations that I have shown you. And to do that, we're going to start with the TDSE, which is the time-dependent Schrodinger equation in the interaction picture. So just to remind you, you have here on the left-hand side IH bar GGT psi IT, where psi IT is the state vector in the interaction picture. And here I have the Hamiltonian of the system in the interaction picture, which is U0 dagger lambda VT U0 psi IT, whereby this is the time evolution operator associated with H naught. So U naught is E minus I H naught T divided by H bar, so that U naught dagger is E I H naught T divided by H bar. So this is our starting point, and we have assumed that we can expand these psi IT into a basis of the eigenstates of H naught. So we're going to consider this expansion, obviously in the interaction picture of Hi into psi k, where phi k are eigenstates of H naught, meaning H naught phi k, ek phi k. That's a definition. So this is what we're going to plug into the time-dependent Schrodinger equation. So we are going to write psi I t sum over k ct phi k. Remember, this is the interaction picture. So plugging this into the time-dependent Schrodinger equation is going to give me I h bar t dt sum of, okay, j, k, whatever you want, doesn't matter, phi j equal to lambda u dagger t v t u t u0 t phi k. So here we wrote our Hamiltonian interaction picture. Here we're considering also I forgot here the sum, sorry. Let me move this a bit because I'm gonna need space. So I'm going to write this as sum over k ct phi k. Perfect. So now if you look at this left hand side, you see that the only part that is depending on time is this guy. So I can write this as I h naught sum over j, and I'm going to make cj dot, which is the time derivative of cj phi j. It's equal to sum over k. I'm putting this lambda here because it doesn't matter. U dagger t vt ut here, not u naught, please note this is a difference, ckt phi k. I'm going to use now the fact that these eigenvalues and these eigenvectors obey certain rules. Namely, I'm going to use the orthonormality, orthonormality of phi j, and I'm going to multiply from the left with phi m of this basis. So I'm going to have an arbitrary eigenvector phi m, and I'm going to multiply it from the left. I'm going to use the bra. And this is going to give me then I h bar sum over j cj dot t. And we have this inner product phi m phi j, which is going to be then delta mj, which is because of this orthonormality. So we have the Kronecker delta here. And here we're going to have equals to lambda sum over k phi m u0 dagger t vt u0 t. I can even keep this here. Let me make space. ckt phi m, and here I have phi k. All right, so we're almost there, because we can see that here on the left-hand side, the only term that is going to survive because of the Schrodinger delta is that the term where m is equal to j. So we can write that this is ij cm dot t. And on the left-hand side, on the right-hand side, we can do the following. We can apply this here and this here. So we have lambda sum over k ckt phi m e I h naught t divided by h bar. So I'm applying this guy here, this operator to this. And here I'm going to have the rest. So vt u naught, which I'm going to write also e minus I h naught t divided by h bar phi k. So I'm going to apply this to the right. So because these are the eigenstates of h naught, when you apply this, you're going to find that u0 dagger, which is the time evolution operator associated with h naught, applied to phi m to the left, is going to give you e I e m t divided by h bar, where this is an eigenstate of this Hamiltonian, so it's an eigenenergy. So we keep this here, and when we apply to the right, we get e minus e I minus I e k t h bar phi k, whereby ek is the eigenenergy associated with phi k. Pull this out. These are just numbers now. These are just phases. So this means that we can write this part as e I e m minus e k t divided by h bar phi m v t phi k. This is a matrix element v m k t, and we can call these here. We define E n minus E k divided by h bar. This is a Bohr frequency, omega n k. So let's have a look now at all these, and we can rearrange things, meaning that our right-hand side of the time-dependent Schrodinger equation in this basis is going to look like this. Is going to be lambda sum over k e I omega n k t v m k t c k t. So bringing everything together, then we can say if we divide by I h bar, that cm dot t is equal to lambda divided by I h bar sum over k c k t e I omega, here's a name, m k t v m k VMKT, whereby VMKT is this matrix element of this operator. So just to specify and make it clear, this is psi m VT phi k. So with this, we can see that we can reduce in the interaction picture the time-dependent Schrodinger equation to coupled differential equations. Because we are working in interaction picture, they don't depend on H naught. And so far, these are exact. So this is important. So far, this expression is exact, because when you do this expansion or when you write these things down, you are not making any approximation. You can expand any state space vector in whatever basis you want. But then you have to be careful what you're going to do with it. So the next step now that we're going to see is how we can treat this perturbatively. So we're now going to do a perturbative expansion. So now is the time to perform certain approximations. And what is going to happen then is that we are going to use this dependence on this arbitrary parameter lambda to expand our coefficients CMT, which are carrying the time dependence of the problem. And this means that we are going to write CMT as Cm to the power 0 t plus lambda Cm1 t plus lambda square Cm2 t, etc., etc. So this is going to be sum over j lambda to the power j Cm jt. And don't forget that these coefficients are key for the time dependence. So we're going to insert these in the time dependent Schrodinger equation once more. So remember that we had an expression already as a function of each coefficient CMT. So we're going to have d dt sum over j lambda j Cm jt is going to be equal to lambda over I h bar sum over k exponential of I omega mk t, where these are the Bohr frequencies, time vmk, which is this matrix element of the interaction. And here we have, I'm putting n lambda n c k n t. So I'm considering expansions here on the left hand side and here on the right hand side. And we know that this equation should be valid for any value of lambda, so that we will equate powers on the right hand side and the left hand side. Now, this is clear because if you would like this to be valid for any value of lambda, this equality that we have here has to hold term by term. Do you agree? Okay, so we can even make this nicer, but we can see already that we have here on the right hand side one more lambda, which we need to take into consideration. And I'm going to write the expressions order by order. So let's have a look what you have for zero order. So for the 0th order term, you have, remember, this is when j is equal 0. So if you look here on the right hand side, you don't have any term which has lambda to the power 0. So we know that for 0th order, we're going to have that Cm0 dot, where the dot indicates time derivative. This is equal to 0. So just to make it nicer here, I'm going to write this guy as sum over j lambda j Cm dot jt. It's a bit clearer, but it's pretty much the same. Now we need to consider the other orders to see what we're going to obtain. So for first order, we can see we get something from here. And we have already here something multiplying. So we're going to have that this n has to be 0. So this actually means that for first order, j, which is the index we are using on the left-hand side, is equal to 1, and n is equal to 0. And this is going to give me then the term, this is in the term in lambda. So I'm going to have Cm dot 1t 1 I h bar sum over k e I omega mkt v mkt ck 0t. Now we can carry on. Second order, we just have to equate left-hand side, right-hand side terms to the power 2 with regard to lambda. So for the second order, we're going to have that j, which is the index we are using on the left-hand side, is equal to 1, and n, which is the one on the right-hand side, is equal to 1, because then we get 1 from here and 1 from this sum. So n equal 1 gives you lambda. Multiplied with this, you get second order. If you have then j equal 2, you have lambda square here. So actually, I don't know what 1 is doing here, should be 2. So you are going to find from the left-hand side that Cm dot 2 is 1 over I h bar k e I omega mkt v mkt CK1T. And we can carry on and carry on until we have, for a generic nth order, Cm dot n 1 over h bar, ih bar, sum over k, exponential I omega mkt vmkt ck n minus 1t. So we can see that we have a recursive relation that we can in principle apply and get corrections over lambda to any arbitrary order we would like to have. But we're going to be modest. We're going to do for the first and second order, but it's important to bear in mind that this is a recursive relation connecting nth to n minus first order.